Let us go back to the material. So I have one bonus question for you. Okay, take this chance. Why this formula has a parameter eta 0 here? Do you know what is this? Yes. Resistance. What resistance? The resistance of a piece of resistor, or the resistance of? Okay, so the resistance, wave impedance, right? Wave impedance of air, right? Very good. Okay. This is wave impedance of the air. Well, what's the number? Do you know? How many ohms? Good, 377, right? So this is a constant. You do not have to calculate it, just look at the table. But why a 377 ohms here? That's my question. The formula is about the relation between electric field and the light intensity. Light intensity can be translated to power density, the power per unit cross-sectional area, right? But why the relation is governed by a wave impedance there? Do you know why? Think about the electromagnetism you studied maybe many years before. Remember, light or laser is about electromagnetic wave, right? So you have electric field, you have magnetic field, right? But here we calculate electric field. And the light intensity should be about both electric and magnetic field. Excellent. Poynting theory, right? As you will see shortly after, the Poynting theory is about the power density is the external product between electric field E and the magnetic field H, right? But we know magnetic field is related to electric field by wave impedance. So roughly speaking, you got E cross H can be translated to E cross E over this one. So you have E squared. That's why you have a square root here. And that's why you have a wave impedance here. So it comes from the the Poynting theory. Excellent. Okay. Good. Next, I will show you one example such that those formulas would be more impressive for you. Okay. A fiber laser in my lab. Okay. So some students in my research lab made a passively Moorlach Erbindorf fiber laser several years before, and they measure the following parameters. First, the repetition period is 176 nanosecond. Okay, the pulse duration, as shown in this figure, is 156 femtosecond. The FWHM is here, but you know this shape is not a perfect Gaussian. It has some oscillating tail here. Okay. The central wavelength is 1560 nanometers, as shown in this figure. So you can use an optical spectrum analyzer, directly measure the power spectrum of the laser pulse. You got this one. Central wavelength is about here, 1560 nanometers. And then you can use a power meter, knowing that the average power is about 67 milliwatts. Okay, so it's a very simple fiber oscillator in my lab. And these numbers can be easily measured, except for this one. You need some knowledge and technique to get this number. Otherwise, all the others could be easily measured. Then my question is, what are the corresponding parameters in the previous slices? For example, you can know the repetition rate, which is 5.7 megahertz. How do you get this number? From the 4 parameters I show you in last page. 这个怎么来？重复率怎么来？
1 divided by repetition.
Good. In last page, I show you the repetition period. Just take inverse. You got the repetition rate. Do you know how to get this number? It's very easy. Your laser pulse shine the photodiode and connecting the electric signal to an oscilloscope. You can see a periodic electric signal. You can count the peak-to-peak spacing. You got this number. Okay, very easy. Then you can know the repetition rate. 5.7 megahertz means in 1 second there are 5.7 millions shots. 1秒钟有570万发的 pulse in this case. You can also calculate the duty cycle, which is very small, 1 millionth. Okay, so roughly speaking, 这个雷射只有100万分之一的时间有 power， 其他都是暗的。Okay. By the central wavelength, you can calculate the carrier frequency, which is very high, 192 terahertz. Okay, T means 10 to the 12th. Okay, and from this number, taking an inverse, you got carrier cycle, which is 5.2 femtosecond. That means if you can trace the electric field, the peak-to-peak or valley-to-valley spacing is very small, only 5.2 femtosecond. Okay, and with pulse width and carrier cycles, you can calculate the number of cycles. In this case, it's about 30 cycles. With 1 shot under the envelope, there are about 30 carrier cycles beneath. Okay. The pulse energy is 12 nanojoule. How to get this number? You have average power, right? You have repetition period. A simple division, you got pulse energy. Okay, 12 nanojoules. It looks very small, right? Nano means 10 to the minus 9th. This is a small number, but considering this energy concentrate within a very short time period, right? So the peak power is actually very high, 47 kilowatts. 47000瓦 ，OK。那 average power 虽然只有 milliwatts 的等级，但是因为 duty cycle is only 1 millionth, so the amplification effect is very evident. You got 47 kilowatts peak power. Okay, and this number is under the measurement. The adjustment factor is 0.62, considering the specific pulse shape obtained from our measurement. 因为这个形状的关系，所以那个小 a 比1小很多哈，它不是1，它只有 0.62。我已经考虑这件事了哈。Peak power 有47 kilowatts. Okay. Then, if you further considering the focusing of the laser beam to a spot of 10 microns in diameter, this is not very difficult. Use a short focal length. You can easily focus the laser beam to this size. Then you got effective cross-sectional area 4 times 10 to the minus 7 centimeter square, such that the corresponding peak intensity is as high as 10 to the 11th watt per centimeter square. And the corresponding electric field, peak electric field, is 10 to the 7th volt per centimeter. Maybe you have no sense about how strong this electric field is, right? Just a number. So I show you one comparison. Okay? The electric breakdown of air occurs at this electric field, 3 times 10 to the 4th volt per centimeter. So that means if you have a parallel plate capacitor, spacing is 1 centimeter. If the applied voltage is, this is 30,000 volts, 30,000伏, then air will break down. Air is supposed an insulator, but under such a high electric field, it can be ionized. It becomes conducting. It's no longer an insulator. So in theory, this is a very high voltage, right? Very high electric field, right? 这个电场已经大到可以让空气从绝缘体变成什么导体，这是一个很大的数字。But this number is even higher, right? Compared with this number, is hundreds of times bigger. So with a very simple laser oscillator, very simple focusing, you can easily achieve a very strong electric field, well beyond the breakdown electric field. Okay. Any question? No? Good. 好，所以我主要说的是什么？一台小小的雷射，然后做简单的聚焦。只要它是一台脉冲雷射，它其实可以得到很强的瞬间电场，大到远比这个介电子崩溃的空气的介电子崩溃电场还要大数百倍。Okay, this table summarizes the time scales, the time span of a pulse. The first column shows the time span of a pulse. Let's assume the pulse duration delta t is 1 nanosecond, 1 picosecond, 1 femtosecond, or even 1 attosecond. Okay? Then you can compare the spatial extent of a pulse. C times delta t. What does this mean? This is easy. In the time domain, the span of a single pulse is delta t. What is C times delta t? C is light speed in vacuum. So light speed times the time duration means what? The length, right? Spatial extension. It means if you have a camera, very good camera, you can take a snapshot about your laser pulse. Then, in that instant, in the spatial domain, it lasts this distance. OK? 你有一台很快的相机好了，你拍你的雷射脉冲，一瞬间照下来，是空间上它有多长？这个叫做 L. Okay? So if your laser pulse is 1 nanosecond, your camera will give you 30 centimeters, like this long. Okay? And the corresponding event is the clock rate of computer CPU. Okay? 你目前的 either laptop or your smartphone, the CPU, the speed is about gigahertz, right? So the time domain is nanosecond. Spatial extent, 30 centimeters. Okay. But if you reduce the time span to 1 picosecond, 10 to the minus 12th second, your spatial extent reduces to 0.3 millimeters. You know 1 millimeter, right? the finest scale in your ruler. It's only about 30% of that unit. It's very small. Okay? And the corresponding physical event is rotational dynamics of many molecules. 很多分子它的旋转周期大概在这个 order, picosecond. Okay. If you further reduce the pulse duration to 1 femtosecond, spatial extent 0.3 microns or 300 nanometers. 所以1飞秒的脉冲，空间上只剩下300纳米，好短好短。Okay. Corresponding event, vibrational dynamics of molecules. It's rotational, this is vibrational, they are different. 什么是 rotational? 就整个打滚啊。Vibration 只要震动啊，这个当然笨重一点啊，慢一点，这个比较快。Okay. But they are about molecules, 分子。If you reduce your time span to attosecond, 1 attosecond, 10 to the minus 18th, spatial extent is crazy small, 3 angstrom. 1 angstrom is about the size of a single atom, right? 3 angstrom means the laser pulse extend only 3 atoms. Okay, very, very short. And this speed is about the electronic motion in atomic scale. It's the motion of electron. You know electron is very light, 很轻，对不对？所以它的速度是很快的，比分子要快很多。So if you want to observe electronic motion, you need attosecond pulse. Then femtosecond pulse is no longer sufficient. Okay. So as the event is faster and faster, you need shorter and shorter pulses. Okay. Any question? Good. This slide shows the time scales of molecule and the atomic dynamics. 2 examples. First, water molecule. You know water molecule since the middle school, right? H2O. You have 2 hydrogen atoms, 1 oxygen atom. So the red one is oxygen atom. The white ones are hydrogen atoms, right? This is a single water molecule. There are many different vibrational states like symmetric stretch, asymmetric stretch, and bending. So the water molecule may have different vibration states, and they behave different period. 就是说，它一个周期跟它一个周期跟它一个周期都不一样。For example, asymmetric stretching, this one, the period is 9 femtosecond. So that means if you shine a laser beam on water molecule, and if the wavelength is correct, this one, okay, then the wavelength will synchronize with the oscillating period. Then there will be strong absorption. The laser energy will be strongly absorbed by the water molecule. So as the output, you got the weak output signal. But if you change the laser wavelength away from the resonance, the absorption is very small, you got a high output. Okay? So you can use a tunable CW laser to observe which vibrational state is the water molecule. Okay? But you know, to this point, we do not need femtosecond laser. You just need a CW laser with tunable wavelengths. You can tell different vibration states, right? A second example, hydrogen molecule. It has, similar to the water molecule, has different vibrational states. roughly speaking, vibrational period is 8 femtosecond. Okay? But if you look at electron period, it's not the vibrational period. Electron period means the motion speed of the light electron. 很轻的电子在动，当然是快很多。How fast? The period reduces to 26 attosecond. So clearly, if you want to observe electronic motion, you need a laser pulse as short as 26 attosecond. Okay? But if you just want to observe the vibrational states of water molecules, maybe femtosecond pulses should be sufficient. Okay, so next, the shortest pulse ever generated by human being in the UV to near infrared regime. Okay, so I think I update this slide based on the latest research publication. Okay. So starting with very intense 25 femtosecond pulse at 800 nanometers. Basically, it's a disulfide laser. You can purchase a laser source if you are rich. Okay? Then you need a hollow core fiber filled with neon gas as nonlinear medium, because this is only 25 femtosecond, not short enough. So you shine the pulse, interacted with the neon gas for nonlinear interaction. Then you will have a very broad output spectrum. Okay? Let's check the longest and the shortest wavelengths. Longest is 1300 nanometers. It's already infrared, right? 230, of course, is UV, ultraviolet. So it's from UV all the way to ultraviolet. It's a very broad bandwidth. If it is not clear enough, I will show you another assistant information here. This is the visible light. The reddest one is about 700 nanometers. The violet is about 400 nanometers. So this is already the entire visible. That means this is white light, right? If you have everything over this range, you have white light. And this is the bandwidth generated in this case. It's even whiter than white light. 比白光还要白的光，对不对？因为频宽更大了。So it's amazing broad bandwidth that you can generate. But if you stop here, you cannot have short pulse yet. What do you need further? You need 4-channel synthesizer. What does that mean? This bandwidth is too broad. You have nothing. You have no tool to manipulate this bandwidth. So you have to divide and conquer. You need the first pulse compressor covering this range, second compressor, third compressor, and the fourth compressor. One by one, you can clean up all the phase curvature, making them perfectly flat. Then combining all these frequency components, you can get a short pulse. Okay. If you leave it alone without this one, just stop here. Although the bandwidth is very broad, but in the time domain, it's not short pulse. We will analyze this aspect later in this lesson. Okay. So it's technically difficult. You need starting with a short pulse laser, nonlinear interaction, phase compensation. Okay, if you can do everything, then you got this crazy number, 380 attosecond in time domain, the pulse duration. Okay, 380 attosecond. Okay. And this work was published in last year. Okay. So maybe we can do better if you guys work hard enough. Okay, next, let's talk about the characteristics of ultrashort pulses. The reason is later we will talk about the applications. Okay, but you know applications depend on the characteristics. 你有什么特征，你就能做什么特别的应用啊。所以我们先从特征开始啊。这些超短脉冲雷射有什么特征啊 ？First, fine time resolution. If you have a very short pulse, you have very fine time resolution. 很精密的时间解析能力啊。So how fine can you get? In last example, since the pulse duration can be as short as 380 attosecond, right? So roughly speaking, time resolution can be better than 1 femtosecond. Okay, so you have a very fine ruler in time domain. Okay. And if you have very short pulse duration, in other words, you have very broad bandwidth based on the Fourier transform theory, right? Short time duration must correspond to broad bandwidth, but not vice versa. Broad bandwidth does not guarantee short pulse duration. Okay, so we will analyze this issue later. So if you have 1 femtosecond pulse width, roughly speaking, the bandwidth is the inverse. 1 femtosecond inverse means 1 petahertz, 10 to the 15th hertz. Okay, just like the previous example. Yeah. Here, the bottom axis shows the frequency, absolute frequencies, starting from maybe 0.3 petahertz all the way to 1.3 petahertz. So the bandwidth is 1.3 minus 0.3. It's 1 petahertz already. The bandwidth is crazy broad. Okay. Okay. The second characteristic is you can have high peak power. Currently, the strongest laser in this world can reach a peak power about 1 petawatt, 10 to the 15th watt. Okay, there are several strong lasers in the world, around 1 or 2 or several petawatts, okay, including one in mainland China. Okay. The corresponding peak electric field can be as high as 10 to the 13th volt per centimeter. Okay. If you come from the physics major, maybe you can roughly sense how strong the electric field is. The electric field is so strong that it can overcome the atomic bonding force, maybe. Okay. So that means if you have femtosecond laser sources, you can do something very cool, very unique, since you have fine time resolution, ultra broad bandwidth, and ultra high peak power, right? So you can do something cool. And in terms of high peak power, I want to show you a number for comparison, because otherwise, this is just a number. You cannot sense how large it is, right? So for comparison, I show you this number. The total electricity capacity of the world is 5.5 times 10 to the 12th watt, according to a number in 2012, several years before. 所以全世界的发电总容量是这个数字。And for a single high power laser, the peak power is this number. So you can see it's about 200 times larger than the total electricity capacity of the entire world. Okay. But of course, this is average power, and this is peak power. Okay, but simply speaking, you can use this laser source to do something that even the entire world electricity capacity cannot, at least for a very short moment. Okay. So it's truly a very high peak power.